Then you can get into the moment for, I'm going to say uniform shapes. Or I'll say uniform, I'll say shapes. It basically means solids. Solid objects, right? So a solid object has mass distributed around it, and you can imagine probably the way you would calculate the moment is by treating that solid object as a bunch of little masses and getting their moments and adding them up. And you know what that's going to lead to. Oh, you have to do an integral, right? Oh, I saw a perfect reaction. Oh, it's perfect. So we're just debating in this class, do we want to do that or not? It's sort of an engineering thing. Even when we do it for the engineers, we just give them the formulas for the standard sizes anyway, shapes anyway. So right now I'm just going to give you the standard formulas, and they are insightful. Here's a ring, a thin ring. Thin ring. We're looking at this axis along here. Around the axis. For a thin ring, all of its mass is at the same radius. It's like a series of particles all at r. And if one particle is mr squared, then this one just must be mr squared. Okay. There's no, like all the answers are going to be something times mr squared. But that one is just mr squared, because basically all the mass is at r squared. Oh my God. Oh, sorry. Yeah, so I missed a bunch of questions. It's not making noise. Okay. So that was a ring. I'll answer these later. Now let's look at another shape. The most important shape in any physics class is a disk. All right, so let's look at the moment of a disk. There we go. So a disk has some thickness like that. It has some radius r and some mass m. And maybe right away you can guess, is it going to be bigger than mr squared or is it going to be smaller than mr squared? It's going to be smaller because all the mass isn't at r. Some of the mass is close to the axis of rotation, which is again like there. So it's 1/2 mr squared. We could do a big integral in 3D to get that. Trust me, it's 1/2 mr squared. Let's see. So let's look at a cylinder. Like this. Ooh, look at that. A cylinder through that axis going around as you would expect. Now it has height h and radius r and mass m. What is the moment? You could print it on the cylinder because it's bigger. It's also 1/2 mr squared. It's the same thing. The height doesn't matter. Okay? Because here the mass is distributed in a certain way around this axis. Here it's the same. It's distributed a certain way around the axis, and the same fraction is close and the same fraction is far. And where it is in this direction is irrelevant because that is along the axis direction, right? So it's where it's distributed really perpendicular to an axis. It doesn't matter if the mass is spread along the axis or not. Okay, so if you ever have a problem with a big long cylinder, realize, it's the same as a disk. Okay, they're the same thing. No difference. Let's look at a rod. Here we go, a thin rod. And if we go through the center of the rod like that, and the rod has length L like that and mass m, it is 1/12 ml squared. Why is it so low? Why is it a 1/12? It's because we're calling it in terms of L and not radius is part of the reason. See, everything else is a radius. This actually has a diameter. So if you call this L over 2, then the 1/12 wouldn't be so big. So that's the only reason there's a big 12 there. Right? Again, we could do an integral to get that, but I'm just telling you. Okay. And then the sphere. We could do an integral in spherical coordinates. It's online if you want to watch me do it. And I screwed up on purpose for educational purposes, but I really screwed up on accident, and then I made a second video. So if we had a sphere of radius r, big mass m, the moment, and you need this for the homework, is 2/5 mr squared. How do we get 2/5? Well, it's a bunch of integrals in spherical coordinates. Let's see if any of these are answerable at this point. The subscripts in the formula for inertia, yeah. So these i's, this is like if we're adding up a bunch of masses. So this was I equals 1, I equals 2. Really just add up all the masses, just like we added them there. That's what that subscript was. Is L a vector? No. So in this case, L is just this distance, and since we're going to square it, we don't care about direction. So if you're asking if L is a vector, you're thinking about if the direction matters, and it doesn't. Right? Will the stick have bigger or smaller moment if the point mass than or less moment for a point mass than a skinnier stick? I'm not sure exactly what you mean. Here I was ignoring the stick. All right, so the stick is thin compared to this is really heavy mass. It's a really light stick. Okay? Okay, so those are the fundamental moments. Should we memorize these for the exam? They're on the equation sheet. So you don't have to memorize them. Well, we need to know how to do integrals for the moment of inertia. It's not on the homework, and it wasn't on the pledge problem. So it might be in this lecture, depending on how fast we go. But yeah, we don't consider that a huge deal, so I don't think we're going to do that. Let's see. Okay, so now what we want to do is see how we're going to use this information. Oh no, we want to do the, let's see. This first half has been fun enough. Let's save that for next half. So the second half is more fun.